Alright, in this video we prove a theorem about the existence of solutions for a set of simultaneous linear equations like this. So if you express these equations in terms of matrix and vectors like this, the solutions exist if and only if the rank of this coefficient matrix is equal to the rank of the augmented matrix, combining A and these constant terms. And if the solutions exist, then the degree of freedom, which is the number of free parameters in the solutions, is given by the difference between the number of unknowns and the rank of the coefficient matrix. Okay, let's start. Before diving into the proof, let me explain what we mean by the solutions and the degree of freedom by considering simple examples. The first example is this set of simultaneous linear equations. So if we express these equations in terms of the augmented matrix, we have this matrix. To this, let's apply a series of elementary row operations. First, add to the second row -1 times the first row, we get this one. And to this, let's multiply the second row by -1/3, and we get this. Then add to the first row the second row times -1, then we get this. So this is the reduced row echelon form of the original augmented matrix from which we get these solutions. So in this case, the solution is unique. We have x is 3 and y is -1. The second example is this set of equations, which can be translated into this augmented matrix. And to the second row, if we add -2 times the first row, we get this, which is already in the reduced echelon form. The last row is only zeros, and the first row is this. So we have only one equation. So if we set y equals to any constant, let's say c, then x can be represented as 1 minus 2c. So there is one free parameter here, c. In this case, we say there is 1 degree of freedom, or the degree of freedom of this solution is 1. In contrast, in the last example, there are no free parameters. The values of x and y are just fixed. So in this case, the degree of freedom is 0. And the last example is this set of equations, which can be translated into this augmented matrix. To the second row, we add 2 times the first row and we get this, which is in the reduced echelon form. And this matrix corresponds to these equations. But look at the second equation here. We have 0 equals to 4, which is a contradiction. So there cannot be any solution for these equations. So for a given set of linear equations, we may have solutions. If we have solutions, the degree of freedom may be 0, 1, or even more. Or we may not have any solution. Now let us prove this theorem. Given a set of simultaneous linear equations, solutions exist if and only if the rank of the coefficient matrix is equal to the rank of the augmented coefficient matrix. And if the solutions exist, then the degree of freedom of the solution is given by the difference between the number of unknown variables and the rank of the coefficient matrix. First, let us note the following fact. If we are given a set of simultaneous equations like this, linear equations of course, we have this augmented matrix, which can be reduced into the reduced echelon form, let's say A prime and B prime, which corresponds to another set of simultaneous linear equations. And these two equations, this and this, they have the same solutions. In other words, by a series of elementary row operations, the solutions are conserved. For this reason, we may assume that this augmented coefficient matrix is already in the reduced echelon form to begin with. So suppose we have the augmented coefficient matrix, which is already in the reduced echelon form like this. So this is the first pivot, second pivot, and so on. This is the rth pivot. And this element can be either 0 or 1. So we consider these two cases separately. So the first case is when this element is equal to 0. In this case, each of these rows corresponds to one of the following equations. So the first row corresponds to this, the second row corresponds to this, and so on, and finally the rth row corresponds to this. So we have some similar expressions here in each of these equations, which correspond to these columns, which are non-pivot columns. So let's set the unknowns corresponding to these non-pivot columns to some constants. So let's say x c1 plus 1 is set to lambda c1 plus 1. So this is an arbitrary constant. And similarly for other variables, we set like this. And using these constants, all the other unknown variables can be expressed like this. So b1 minus some constants, and b2 minus some constants, and so on and so on. Here, the number of variables is n. We have n unknowns, and we have these r equations. So there are r equations. So the number of free parameters is n minus r, because the remaining variables are just arbitrary constants. So this R is actually the rank of the matrix. So R is the rank A, because this R is determined only by this part of the augmented matrix, which is the original coefficient matrix. That is the rank of A. So this is the degree of freedom of the solutions in this case. Degree of freedom of the solutions. Now let's consider the other case, that is br plus 1 is equal to 1. By the way, in this case, b1 is equal to b2 is equal to all of them up to br, they are 0. In this case, this br plus 1 is 1, but this part, this row, all other elements are zeros. So that means we have 0 equals to 1, which is a contradiction, so there cannot be any solution for this. Also, in this case, the rank of the augmented matrix is r plus 1, because there are r plus 1 rows that contain non-zero elements. This is, of course, greater than r, which is the rank of A. So this is not equal to this. So we have shown that if solutions exist, then the rank of A should be equal to the rank of the augmented matrix. And if the rank of A is not equal to the rank of B, then the solutions do not exist. That means the converse is also true. And we are done.